Welcome to our unit on differential equations and techniques of integration. We're going to start by talking about differential equations. And with differential equations, we've actually been introduced to this idea before. I just didn't use some of this vocabulary. A differential equation is just any equation that has a derivative somewhere in it. It tends to be first derivatives, but it can be second derivatives, third derivatives, fourth derivatives. Just somewhere in the equation, a derivative appears. So even when I see something like dy dx is equal to x, this is a differential equation. We have different ways of solving differential equations. The way we did it in the past is we just said, well, we're finding antiderivatives. In what the example I've written there of dy dx equals x, we said, well, what do I know has a derivative of x? Which would be y is 1/2 x squared plus c. Remember, the plus c is needed because of the fact that we don't know an initial condition for the or a point that our function has to go through. So I have to include all the infinite number of functions, because remember the derivative of c is 0. But in this section, I'm going to introduce a different way of solving a differential equation, which is used on what are called separable differential equations. And it's the idea that we want to get all of our variables, all of one variable on one side, all of the second variable on the other side of an equation by using multiplication or division. And this includes the pieces of Leibniz's notation. This is a Leibniz method. So dy dx, we had said, is the notation that Leibniz is using. And the idea of it is, well, if I multiply both sides of my equation by dx, I'd have dy is equal to x dx. That's the separable part. And then on the next slide, I have a vocabulary that explains what would I do with this to actually solve it then. We are going to be dealing a lot with general solutions here. So we need to remember the plus c. We've gotten out of the habit of it because of definite integrals and the plus c canceling, but plus c is rarely going to cancel now. So we need to start remembering to include our plus c as we find our antiderivatives. And then we will be given points sometimes where it'll allow us to figure out what c is. So I want to introduce the idea of an indefinite integral. This is an integral without bounds. So definite integrals, we had lower bounds, upper bounds. Indefinite integrals are, well, I don't have bounds. So remember I had said, well, we have dy dx is equal to x. Separable means that I could multiply both sides of the equation by dx, get dy equals x dx. But then to solve this, I can do what's called an indefinite integral, because really what I want to do is I want to undo the derivative. Well, remember from our fundamental theorem of calculus, what undoes a derivative is an integral. But I don't have any bounds for it, so I'm just going to leave the bounds off of it. So on the right-hand side, the integral of x is saying what has a derivative of x. Well, that would be 1/2 x squared. And then here, there's really a 1 in front of the dy, so I'm saying the integral of 1 with respect to y is saying what would have a derivative of 1? Well, in terms of y, that would just be y. Now, I do need to remember a plus c. I'm only going to put the plus c on one side of the equation, just because I could say, well, y plus some constant c1 is equal to 1/2 x squared plus some constant c2. But then to isolate y, I'd have 1/2 of x squared plus c2 minus c1. But a constant minus a constant is a constant. So we just save ourselves all of this work, and we just automatically put the plus c on the side with the independent variable x.